First of all, welcome to all of you. As Carmen just mentioned, today I'm going to talk about co-crystal phase diagrams and how we can actually use those diagrams in the context of dissolution studies, so to understand dissolution studies. I will mainly focus on pharmaceutical compounds because that's what I do and that's where I come from. My university is located in Belgium, in Louvain-la-Neuve, which is right under Brussels, so quite central between Netherlands, France, Luxembourg, Germany. And my personal expertise is that actually prior to coming back to university, I worked as a team leader in a pharmaceutical company, UCB Pharma, which is located also in Belgium, where I was responsible for process optimization, working on crystallization processes, polymorphism issues, etc., which explains why I'm still in the field of pharmaceuticals. I mainly worked in upscaling, so getting a crystallization from a lab scale up to an industrial scale. So that's what I did, and that's what I also mainly apply when I work on co-crystallization. So I really look at a macroscopic point of view. I'm not really occupied with doing fundamentals like nucleation and crystal growth, but more with a macroscopic thermodynamics, kinetics. I'm now a professor in Belgium in physical chemistry, and I work still in crystallization, working on crystal engineering and looking at multi-component organic compounds. Now, when I talk about co-crystals, just to make this clear in the beginning, is that it's crystals containing two components without hydrogen transfer. So I'm not talking about salts, I'm really talking about hydrogen bonding without any hydrogen transfer between. Also not talking about any solvates. There's a nice article out there by the group from Nijmegen, from Elias Vriek, which talks about nomenclature if you're really interested in trying to define those names. But I'm really going to be interested in co-crystals. Now, what my group is concerned with is, first of all, how do we identify the different co-crystals? So if you, for instance, take a drug compound, what would be a good co-former? Then we work on how do we get it. It's okay if, for instance, you take one drug, you couple it with citric acid, it gave a positive hit, but how can you make it on a kilogram scale? That's developing a co-crystallization process. And then we're going to go beyond. And what we actually want to do is we want to look at how the co-crystal can be used in applications, chiral resolution, but today I'm mainly going to be concerned with dissolution of pharmaceutical compounds. So let's kick in by making phase diagrams. So if you construct a co-crystal phase diagram, what you actually do when you look at a co-crystallization process is that you take one component, a second component, you add it to solution, and then you apply a normal crystallization process. So you would say, okay, I'm going to cool it or evaporate solvent, and I hope at the end that I get out my co-crystal. Now, when you talk about crystallization process, like you would do for any other compound, what is important is thermodynamics. And what thermodynamics tells you is, where do I end up? What is my final most stable state? Is my co-crystal suspension in solution a stable state? What is going to tell you that? Phase diagrams are going to tell you whether or not you have a stable state. Then you also want to take into account kinetics. Kinetics is the road to get there. How do I get to my stable state? It's a little bit like for polymorphs. Thermodynamics would tell you which is the most stable polymorph at the end. Kinetics is the road to get there, so you might pass through an unstable polymorph. It will be the same idea with co-crystals. Now let's kick off first with thermodynamics and let's look at phase diagrams. Technically, if you would make a phase diagram of a single compound, you would look at the amount of compound, the amount of solvent, and the temperature, which is also what we do here. We look at the amount of compound A, the amount of solvent, the temperature, but we also have the amount of compound B. So this gives us an extra variable. Now, that's too many variables to present in a nice, easy to understand manner. So what we actually do is we're going to reduce one variable. I'm going to reduce a temperature. So I'm taking everything at a fixed constant temperature. If you want a diagram at a different temperature, you can just create a new diagram at different temperatures. Okay. What I'm going to do next is a little bit like with a normal, I'm taking this off. What I'm going to do next is I'm going to play with the amount of compound versus solvent. A little bit like I said before, if you have a single compound, you take solvent and temperature, you look at the concentration. Here inherently I can change compound A and B. By dividing by the solvent, I get concentration of A and the concentration of B. This leaves me with two variables, in which case I can easily plot what we call an orthogonal diagram. So I'm going to present this in a constructive manner. So don't forget what we have now: compound A, compound B, amount of solvent, but I'm going to express this as concentration of A and concentration of B. So on the y-axis, I'm going to put the concentration of B. On the x-axis, I'm going to put the concentration of A. What would happen if at a given temperature, let's say 25 degrees Celsius, I increase the amount of B? Well, first of all, you have a very low concentration of B, you have almost no B, and you increase the concentration of B. At a certain moment, B is no longer soluble, and it crystallizes out. So this value here represents the solubility of B. Okay, so once I'm above the solubility, the thermodynamically stable situation would be a liquid phase with B crystals in suspension. Now, doing the same for A, you increase the amount of A up until the solubility of A. Above that, you have a liquid phase and A, which is stable in suspension. What about the co-crystal? Now, why is this red line? First, before I do this, why is this red line going up? It just means that here I see the solubility of A, but I increase the amount of B. So far, the solubility of A does not depend on the amount of B present. This is what is represented by the straight line. This might change in a couple of slides. Now, what about the co-crystal? If you look at the co-crystal is a solid phase, and when it dissolves in two compounds. So the concentration of A and B are important in solution. It's a little bit like when you go back to first year chemistry and you had to talk about the solubility product. And actually, a co-crystal solubility is defined by a solubility product, KSP. Now, what is important to notice then is that your solubility product will, of course, depend on the concentration of A and the concentration of B. But this also means that if you look at the co-crystal solubility, if you look at the concentration of B versus A or A versus B, you get an inverted relationship which leads you to this type of parabolic solubility curve, which responds to the equation of KSP. Once you're above the line, you have your co-crystal, which is stable in suspension. If you're below the line, of course, you too little concentration, so everything is dissolved. Now it's a phase diagram. In a phase diagram where you have zones that touch, you will get what we call eutectics, or you get two extra zones. In this zone, you have a mixture of co-crystal and B, which are stable in suspension. And in this zone, you get a mixture of co-crystal and A, which are stable in suspension. So this is really what the diagram looks like. Now, this diagram technically should be nice in the sense that you could say, okay, but what happens if I would add what you typically would do? I'm a chemist, that's what I would typically do. I would say, what happens if I add one equivalent of A and one equivalent of B? Because I'm trying to make a co-crystal, which is a 1-1 co-crystal, an AB co-crystal. So I add one equivalent of each. If you do that, if you add one equivalent of A and B and you increase slowly the concentration, you always follow this 1-1 stoichiometric line. And you see that this 1-1 stoichiometric line can actually cross the zone where the co-crystal is stable. If this is the case, we're talking about a congruent system, which is quite an easy system because this means that I can always add one equivalent of each and find the zone where the co-crystal is stable. This is sadly enough not always the case. Compounds A and B, let's just say, imagine they're caffeine and maleic acid. Caffeine and maleic acid often have a very different solubility versus a lot of solvents. So what will happen is that often one of your compounds is much less soluble. So you move your solubility curve, your solubility of A, caffeine in this case, to a lower solubility. The rest of the diagram will, of course, follow. Now look at my 1-1 stoichiometric line. When I plot this again, I no longer go directly into the zone where the co-crystal is stable. This is technically a problem because this means that you cannot use one equivalent of each component to guide you towards the zone where the co-crystal is stable in suspension. But we'll come back to this in a second because you can just work with different stoichiometries. Now this diagram I just presented to you is an orthogonal diagram. I think in the context of dissolution studies, such a diagram is very easy to use and to understand. In the context of scaling up, I hardly ever use it. In the context of scaling up, of developing a process, I will mainly use another representation, which is a triangle representation, in which in one corner you put the amount of B, the other corner you put the amount of A, and here you put the solvent. They are inherently the same. Here I included the solvent with A and solvent with B to go from a ternary to an orthogonal representation, but the diagrams are exactly the same. Okay, you can actually look at it. Here you can see if I zoom on this part and I turn it around a little bit, you get an orthogonal representation. I exactly get the same zones as I got in my ternary representation. So there's absolutely, they're identical. It's just a different way of presenting. And there is some nice work from people from Émilie Gagnère and Joop ter Horst on this topic, where you can easily switch from one to the other and have a look at why they are identical. Now, if you would take the triangle representation, you can always also have this congruent and incongruent case. In the triangle representation, your co-crystal is stable in the center. Here I would have A stable in suspension, B stable in suspension, and in the middle I will have the mixture zones. Now, if my 1-1 stoichiometry line, your 1-1 stoichiometry line here, of course, starts from the middle, one equivalent of B, one equivalent of A. If that crosses completely your co-crystal stability zone, then you have a congruent system. If it does not, you have an incongruent system. How can you switch from a congruent to an incongruent system? Well, nothing stops you from changing the nature of the solvent. If you say, I'm working here with water, it is congruent, I'm happy. Imagine you're working with methanol, it's incongruent, why not switch to water? You have a congruent system, might be easier to work with. So by changing the solvent, you can switch from a congruent to an incongruent, or vice versa. How do you make them now? Because this is why most of you tuned in, I suppose, is how do you make these ternary phase diagrams? Well, very easy. They look complicated, but they're not. Imagine what I said, we work at 25 degrees Celsius. The first thing you need is something that keeps your vials or your experimental points at a given temperature. You can, for instance, use a crystal 16 for this. You don't have to change the temperature, but you can block the temperature at different levels. So that's a possibility. Now, what you do is you actually just take a horizontal line. What is this horizontal line? This horizontal line represents a given amount of solvent. If you have a lot of solvent, you have a horizontal line close to the top, less solvent, less solvent, less solvent. So here I have a given amount of solvent. Usually I prefer working in weight percentages. So imagine here you say, okay, I take 80% of solvent, which corresponds to maybe 1 milliliter in each pot. So you take different vials. Here I have 11 different vials, in each of which I put 1 milliliter. And then I will add solid to each vial. How much solid will I add to each vial? Well, I need to keep the amount of liquid constant. So to each vial, which contains 1 milliliter of solvent, I will add, for instance, 200 milligrams of solid. Okay. Which solid? Well, for my first pot, I will put pure A. For my second pot, what I will do is I'll take 90% of A, 10% of B. In this case, I had 200 milligrams, so 90% represents 180 milligrams. 10%, 20 milligrams. I take my next pot. I still keep 200 milligrams of solid, but this time I will add 180 milligrams, 160 milligrams, that represents 80% of A, and I will add 40 milligrams of B. Now, that prepares my pots. Technically, that would leave me with 11 pots where I should see some solid dissolved or solid in suspension in these pots. What could happen now is that everything is dissolved. If everything is dissolved, this just means that you have added too much liquid. In that case, I would just recommend you to repeat the different pots, but put less liquid. So you reduce the amount. You don't put 1 milliliter of solvent, you put, for instance, 800 microliters. Okay, that's something you will just have to find in the beginning. Also, if you put too little liquid, you won't be able to get a nice homogeneous stirring of your little pots. So what we do then is we try to push the system to go to thermodynamics. What I typically do is I take my 11 pots and I heat them. You cannot show this on a ternary diagram because I was at constant temperature. I heat them to dissolve everything. Then I cool to 25 degrees Celsius again, and I let thermodynamics take over. Technically, you can say we wait. We wait until the crystalline phase comes out, which should be the most stable. This doesn't always occur. It's a bit like an unstable polymorph. You could crystallize out something which is metastable. So what we do is we open each pot and we seed typically with every stable phase. So I would take, for instance, the first pot, seed with A, seed with B, and Cocrystal. And then I wait for 48 hours. After 48 hours, your 11 pots should have crystallized. Now what you can then do is you can take the supernatant of each pot and the crystals. You can analyze the supernatant of each pot, and the supernatant composition, you can analyze that by HPLC or by GC. The supernatant, or just by weighing, the supernatant composition gives you a point on the solubility line. Because it's in equilibrium, the supernatant should give you a point on this red solubility line. The crystal phase, you can analyze by XRPD. It'll tell you which zone you're in. These first two pots should give me crystals of A. These two pots should give me a mixture of A and AB. And this pot should only give me Cocrystal. Here I have Cocrystal and B. So the XRPD is nice, and both analysis can be combined. Is there another way of working? Yes. If you don't have an HPLC, there's actually an easier way of working, is that you make your 11 pots and you take this pot. What would happen if to this pot I add solvent? Well, if you add solvent to this pot, what you actually do is you dilute, and you would go to 100% solvent if you would add liters and liters and liters of solvent. But you don't do that. You dilute until everything is dissolved. And you mark this point. This is the dissolution point. Here you can do the same. You connect it, you get another dissolution point. So you can create your solubility lines by diluting these pots. Of course, you can no longer analyze the crystals. It's a little bit destructive. You destroy your crystals. This will bring me to create a ternary phase diagram. We did this on multiple cases. And this has actually been automated with the Crystal 16. It's called a solvent addition method. I think it's worked by Joop ter Horst. You can easily look it up, where they actually put automated solvent addition into their Crystal 16. And so you fixed the temperature, you dilute until you get a nice ternary diagram. Here are some case examples of where I made some ternary phase diagrams. This is with the dissolution method, because as you see, it's between piracetam and calcium chloride. Calcium chloride I cannot see in HPLC. So we use the dilution method. You can see we get nice ternary diagrams. This diagram was done using actually NMR, and this one was done using the HPLC. Of course, if your HPLC method in this case was not so good, you can see you have a little bit more of experimental spread. Okay, now that I told you how that we can make the co-crystals, let's look at solution crystallization. To look at solution crystallization, I told you that what you want to do is you want to use thermodynamics. Thermodynamics and kinetics. Kinetics is the road to get there. Thermodynamics will tell you where you end up. For thermodynamics, we have our co-crystal ternary diagram. Now let's look at if we can plot kinetics in this diagram too. I'm not talking about kinetics of polymorphism. I'm really talking about kinetics of stable phases. Technically, I stopped my line here. When I was above this line, B was stable in suspension. No matter the concentration of A, no matter the concentration of caffeine, as soon as I'm above this line, maleic acid should be stable in suspension. So I can actually continue drawing this line. Nothing stops me from doing that. I do the same for caffeine. As soon as I'm over this concentration here, caffeine is stable in suspension, no matter what the concentration in maleic acid is. This means that if I would place myself in this zone, I could technically spontaneously crystallize out caffeine and maleic acid. I'm plotting my co-crystal, and for my co-crystal solubility curve, I can do exactly the same thing. I can continue pulling this line further down and further up. As long as I'm on that side of my phase diagram, my co-crystal is stable, can spontaneously crystallize out. Now this looks complicated. What I just did is I plotted my orthogonal diagram in which I had zone 1, 2, 3, 4, and 5. And now I cut it in kinetic regions. What do these kinetic regions actually mean? Imagine I place myself in region 1. In region 1, shown here in bold, B is the stable phase in suspension. But in region 1A, B is also the only phase that can actually spontaneously crystallize out. In region 1B, my co-crystal can technically also spontaneously crystallize out. It's just not stable in suspension, so over time it will transform into B. If you would take your zone 3, it's even worse. If I'm in zone 3A, you're supersaturated with respect to co-crystal, so the co-crystal can spontaneously crystallize out. It's the only phase that is stable in suspension. If you're in zone 3B, caffeine can spontaneously crystallize out, but also my co-crystal. Nevertheless, the co-crystal is the only stable phase in zone 3. So even if caffeine would crystallize out, it will over time transform into your co-crystal. And I'm going to show you this. Now, how do you do a co-crystallization from solution? You can do this by evaporation. Evaporation just means that I start with imagine you start with a very, very diluted solution. So there's nothing in there. I start with a very diluted solution, and when I evaporate solvent, I concentrate. I concentrate more and more, and I took a stoichiometry which is 1, 1. So 1 equivalent of caffeine, 1 equivalent of maleic acid. The green dot represents my solution concentration. If you evaporate solvent, you will increase the concentration until you reach the zone where the co-crystal is stable. What I showed you now is a spontaneous crystallization of my co-crystal. Either you seed or you hope it crystallizes. I recommend seeding. Then, of course, if you continue evaporating, you can continue crystallizing out co-crystal. I put the green dot a little further. The green dot represents the overall composition now. So it becomes more and more concentrated. Of course, your solution concentration is given by your solubility line. So you get more and more solid out. What happens if you have an incongruent system? In an incongruent system, you also increase the solubility, you also increase the overall composition by evaporation, but you enter the phase first where caffeine can crystallize out. So technically, imagine caffeine crystallizes out immediately, you get caffeine. You continue concentrating, and then you will enter the zone where the co-crystal and caffeine are both stable in suspension, so you will start crystallizing out your co-crystal also. Let's have a look at what can you do in the last case of an incongruent crystallization. Is that in worst case scenario, if you want to go towards the AB zone, well, why not take a different stoichiometry? Nothing stops you from taking a different stoichiometry. In this case, I showed you a stoichiometry of 2B versus 1A. So I follow a different stoichiometric line and I enter a zone where the co-crystal is stable. So these diagrams really can help you to guide you towards which is the most stable situation. So my guidance here is to say start with an equimolar mixture only if your system is congruent. Try to seed. Always seed if you want to make a crystallization. And these curves can also be used to extract the yield. If you want more information on that, you can either ask me or read up on it. Now, what happens if you change the temperature? If you change the temperature, you keep your overall composition constant, my green dot, but I changed my solubility. So you change your diagrams, you lower the solubility, and you enter the zone where the co-crystal comes out. So it's a little bit different than when we had the evaporation. Now we change the diagrams. Okay. Again, if the system is congruent, cooling is straightforward, and I always recommend seeding. Kinetics. Now about kinetics. I'm taking another aspect now. What if I don't seed? Is seeding that important? Yes. Imagine you're in the zone 3D. Okay, I created a supersaturated solution. How did I create that? I created that by heating up everything and cooling it down again. So it doesn't come out spontaneously. And what can crystallize now? Remember I said in zone 3D you can crystallize out maleic acid, caffeine, or the co-crystal. Now if you crystallize out the co-crystal, my green dot will now represent my solution concentration, what will happen is your co-crystal crystallizes out up until I reach the solubility curve, and I have crystallized out my co-crystal. Is this necessarily the case? No, you can crystallize out caffeine, in which case your solution reduces the amount of caffeine crystallized out. At that stage, my solution concentration is here. What can happen at this point is that I can either crystallize out the co-crystal or maleic acid. At a given moment, I chose to crystallize out maleic acid. This is what I chose in my representation. So I go down up to this point. So even now, if the co-crystal should exist, I ended up with a suspension which contains caffeine and maleic acid. My solution is still supersaturated with respect to co-crystal. So it can at a certain moment appear. I become undersaturated with respect to caffeine and maleic acid because my co-crystal suddenly crystallized. So they both dissolve and my co-crystal continues to grow. So at the end, you end up with the same situation. You end up with what is thermodynamically stable. It is just that you got there in a different pathway. Kinetics guided you in a different pathway, but at the end, if I immediately started with the co-crystal, I would end up with the same final suspension. Thermodynamics always wins, to put it like that. So that's why I recommend seeding. Always seed. It'll guide you towards the thermodynamic endpoint in the most easy, controlled way. And then for the part on dissolution. Dissolution behavior of co-crystals is in literature often described with a spring and parachute behavior. And I'm going to talk you through this type of behavior, which we actually described in a book on multi-component crystals. It's a chapter I edited with Joop ter Horst, so you can have a look at that chapter if you want to know more. And why do we look at the dissolution profile of co-crystals? Well, what you have to know is that 85% of drugs are commercialized as oral drugs. Lately, a lot of them exhibit low water solubility due to the complexity increase of the molecules. So they're classified BCS2. BCS2 means low solubility and high permeability. Now, what you look at when you look at drugs is you want to look at how the plasma concentration, so it's pharmacokinetic studies, how the plasma concentration changes over time. Because what you actually want is you want your drug either to have a long delivery in your body or to have a high concentration at a given moment so that your drug is actually active. How do you do these profiles, these pharmacokinetic profiles? You actually take patients and you take blood on a regular basis after they have been given an oral tablet of a given drug, and you follow the plasma concentration over time. This is not always very feasible or easy or costly. So what you can do is we stick models to this. What type of model would you use? Well, you can look at a dissolution curve. You look at the dissolution curve. So a dissolution curve is just made in, not in vivo, but in vitro. What you do is you take a dissolution vessel. It's a double-checked vessel. You take your temperature 37 degrees, which represents your stomach, and you put a tablet in this. And from time to time, you sample the supernatant solution and you determine your concentration. And this over time will give you a dissolution curve. Now, this can be automated. There's tools now to allow you to automate this. Now, why are these dissolution curves used? These dissolution curves are used to look at to avoid having to do in vivo studies all the time. If you would, instance, have two polymorphs, polymorph A and B, and polymorph B didn't give you a high in vivo exposure, you can take another polymorph which gives you a better exposure. Now, your dissolution curves of both these polymorphs should also show you the same behavior. So here you can see that the dissolution curve of polymorph blue, the blue polymorph, polymorph A, is higher than the dissolution curve of polymorph B. So in this case, these dissolution curves are indicative of what would happen in the body, and that's why we do them. Okay, now let's go back to my dissolution curve and try co-crystallizations. Can I understand the dissolution curve of a co-crystallization? Yes. We're going to use phase diagrams again. Again, remember what I said, we had this temperature effect. Now I feel even more comfortable fixing the temperature because my body is at 37 degrees, so I don't need to take temperature into account. So I would have ideally done my phase diagram at 37 degrees, okay? So I consider all diagrams at 37 degrees. I take my dissolution vessel caffeine, maleic acid. And now I start by putting caffeine in solution. So this is particles of caffeine. Imagine you made a tablet of caffeine, crystals of caffeine. What caffeine will do is caffeine will start dissolving. I only look at caffeine, so I'm on this line. I increase slowly my concentration of caffeine in solution because the crystals of caffeine are slowly dissolving up until you reached the solubility of caffeine. So this dissolution curve is easily created. What about my co-crystal? I put my co-crystal tablet in solution, so I put my crystals here, they are co-crystals, and I start dissolving. Now here on the left slide, I only look at the concentration of caffeine. In my phase diagram, I will of course look at the concentration of caffeine and maleic acid. They are both coming into solution. But on my left slide, I only represent the concentration of caffeine of my API. As soon as I dissolve one co-crystal, I added a stoichiometric amount of caffeine and maleic acid. I dissolve another co-crystal, I increase both in a stoichiometric manner. So I follow the stoichiometric line. On my dissolution curve, yes, caffeine will increase. The amount of caffeine is given by my x-axis. Okay, the amount of caffeine is given by my x-axis. This will continue, of course, up until the point that I reached the solubility line of my co-crystal. Then my solution, that last co-crystal is an axis, it won't dissolve. And as you can see now, my concentration of caffeine is actually lower than the solubility of caffeine. So you reached a concentration of caffeine with your co-crystal, which is lower than the concentration of caffeine on its own. So now you're going to say, why is this useful? Because this will only lead to co-crystals which have a lower solubility than the pure component. Yes, but I ignored to tell you one thing, and as in the beginning I said the concentration, the solubility of caffeine does not alter with the amount of maleic acid. This starts from the idea that they don't interact in solution, which clearly they do if they're willing to go together in the same crystal structure. So often what happens is that these diagrams are a little bit screwed in the sense that they kind of, the solubility here of caffeine will increase when you add an amount of maleic acid. Okay, so this gives you these good diagrams. Now, if you now follow the 1-1 stoichiometry line, you can see that when I add up to the solubility of caffeine, my final concentration in caffeine in solution can actually be higher than the compound itself. So you can use co-crystallizations to increase the solubility. In the book chapter, there are some nice examples on this. I'm going to speed this up. So these, you have examples which are genistein caffeine co-crystals, and there's other co-crystals which are given there. There's a nice summary where you can have a look at. Now, what about incongruent systems? Incongruent systems are a little bit more complicated, but actually occur quite a lot. You cannot change your system now. Don't forget that we're in the body, so I'm stuck with my simulation of my stomach fluid. So I cannot change the solvent. I'm not going to go to methanol here. So I'm stuck with the nature of my solution. I do the same. I add caffeine. If you add caffeine, nothing has changed. Caffeine will dissolve. It will dissolve up until the point that I reach the concentration, the maximum amount of caffeine that I can solubilize in my stomach. Then I do the same for my co-crystal. Nice, you can go up. Same idea. If I go up the stoichiometric line, 1-1 stoichiometry. I increase for one equivalent of caffeine, there's one equivalent of maleic acid appearing. I see my amount of caffeine, of course, going up. I go up very high. I go up very high up until when point? Up until the point that I reach the solubility curve of my co-crystal. Up until this point here. I reach the solubility curve of my co-crystal, and because crystals usually have a tendency of dissolving quite rapidly, this is called a spring behavior in literature. So you have a spring behavior, a very rapid dissolution. And then suddenly what can happen? At this stage in solution, my solution is actually oversaturated with respect to caffeine. Technically, caffeine can spontaneously crystallize out now. And this will happen at a given point. So at a given point, caffeine will suddenly spontaneously crystallize out. My co-crystal, if this happens, my co-crystal suddenly becomes undersaturated. Now, if you still have some co-crystal left, it will continue to dissolve. Caffeine will continue to crystallize out. So caffeine will continue to crystallize out up until I reach the solubility of caffeine. Because your growth of caffeine co-crystals is slower, what you actually have is a parachute type of behavior. So you have like this tailoring off, but this tailoring off is due to the fact that crystal growth is usually slower than crystal dissolution. So we have this nice spring parachute behavior completely explained by ternary or orthogonal phase diagrams. So we have this re-explained in the book chapter also if you want to go through this in a more slower pace. Do we see this? Actually, you often see this. If you go through literature and you look at co-crystal dissolution curve, you often have this spring parachute behavior, which you can then now explain using thermodynamics and, of course, a little bit of kinetics. Don't forget that in this diagram also, I only represented these perfect lines. You can always bend them a little bit to the right if you want to make your solubility of caffeine depend on the amount of malic acid. So this brings me to the end of this webinar. I hope that it was useful. If you have any questions, like Carmen said, feel free to contact them and they will forward it, or you can read the book chapter, or you can always have a look through literature. So thanks for the funding agencies, and I would also like to thank Technobees for giving me this opportunity to present you this webinar.